Assalamualaikum. Bismillahirrahmanirrahim. Okay, today we're going to talk about liquid characteristics and dimensional analysis. Okay, liquid characteristic. So liquids have definite volume but indefinite shape. They are free to form droplets and powders when they are not inside a container. When a liquid is inside a container, it will take its shape. Unlike gases, liquid will not change its volume to spread out and completely fill a container. There is enough intermolecular bonding to give liquids a definite volume. Besides that, liquids are fluid, able to flow and take any shape. This occurs to the weak intermolecular bonding that allows the molecules to slide past each other freely. As a result of being fluid, liquids exhibit many interesting properties that solids do not, including capillary action and diffusion. Furthermore, liquids like gases undergo diffusion when mixed. This can be seen by adding food coloring to water. Different liquids, when added, will cortically spread out and mix together. Diffusion will occur faster when the liquid is warmer because the increased kinetic energy allows the molecules to move faster and collide more frequently. Next, liquids are usually considered incompressible. The molecules are already close together, so it's difficult to compress them anymore. Under a very high pressure, liquid will actually compress, but not very much. Last but not least, liquids, unlike gases, have distinct surface. They need they need not they need not take their container's shape. This allows the formation of droplets and puddles. Next, we will discuss about dimension analysis. What is dimensional analysis? Dimension analysis is a means of simplifying a physical problems by appealing to dimensional homogeneity to reduce the number of relevant variables. A dimension is the type of physical quantity. So we have a example of primary dimensions. First, we have mass. Mass, the unit for mass is kilogram. The dimension is capital M. Also, we have a length. The unit is meter. The dimension is capital L. And then we have a time. The unit is second and the dimension is T. And last but not least, we have temperature. The unit is in Kelvin and the dimension is actually theta. It's not a zero. It's theta. Okay. This is the dimensions of common derived mechanical quantities. So we have four property such as geometry properties, kinematic properties, dynamics properties, and fluid properties. This is the example of the geometry properties, and this is the example for the properties, the quantities of the properties and its dimensions. For example, for the geometry properties, uh, the quantity is area, the dimension is L square. For the kinematic properties, such as acceleration, here is the dimension is LT negative 2. For the dynamics properties such as force, the dimension is MLT negative 2, and the fluid properties, the quantity is a density, and the dimension is a ML negative 2. Yeah, and then there's a okay Radix method. Radix method, a basic method to dimensional analysis method, and can be simplified to yield dimensionless groups controlling the phenomenon. flowchart beside shows the procedure. So here is the procedure for Rayleigh's method. Let's take a look for the example of Rayleigh's method. I will explain more in the example here. So the question is, using Rayleigh's method, determine the rational formula for the power developed by the pump when the power P depends upon the head H, the discharge Q, and the specific weight W of the fluids. Okay, the first step 1, you have to determine which is the independent variables and the independent variables. So in this question, it states that the power P depends upon the head H, the discharge Q, and the specific weight W of the fluids. So basically, here it's obviously that the P power is the dependent variables while the H, Q, W is independent variables. So that's why I write like this. And then in the step 2, you have to write in this form, P equal to function bracket HQW bracket, and then write P equal to KHA QB WC. K here is a constant. And then in step 3, we have to put the dimension of each quantity here. So power, the formula is energy over time equal to half mv squared over time. So the dimensions for the power is m1 l2 t negative 3. And then proceed to the k. K is constant, so the dimension is m0 l0 t0. And then h l1 q, the formula is m cube over second, so the dimension is L cube T negative 1, and the specific weight is M1 L negative 2 L negative 2 T negative 2. And then in step 4, we have to replace all the dimension inside the formula followed by the formula in the step 2. And then after you replace it, you have to simplify it by, for example, here you can times L1 times 1 times A. It's like basic mathematics here. After you simplify it, you can compare it beside in a both side, by both side. So for example, here M with M, L with L, T with T. So here, so M only 1 from this side, so C equal to 1. So after that, for L, next for L, A plus 3B minus 2C equal to 2. And then, but here you have a 2 unknown, which is A and B. So you cannot get the answer. You only have a C. So you proceed with the T1 and the T. Here you have a negative B minus 2C. So equal to negative 3, you can get the value of B. After you get the value of B and C, you can substitute in here. And you get the A, the value of A, which is 1. And then after you get the value of C, A and B, you put them back in the equation here. So you can get the P equal to K H1 Q1 W1. That's why here you get the P equal to K HQ. The second method is Buckingham's pi theorem. When a large number of variables are involved, Rayleigh's method becomes likely. In such circumstances, the Buckingham's method is used. This method expresses a variables related to a dimensional homogeneous equation. So this is the example for Buckingham's method. So the question is obtain an expression in a dimensional form for the pressure gradient in a horizontal pipe of circular cross section. Show how this relates to the Fabry expression for frictional head loss. So step 1 you have to identify the relevant variables. For this question, the relevant variables is dp over dx, density, velocity, diameter, ks, and viscosity. And then step 2, write down the dimension of each of the variables. So dp over dx, this is the dimension, followed by the density, velocity, diameter, ks, and viscosity, and its dimension. And then step 3, we have to establish the number of independent dimensions and non-dimensional groups. Number of relevant variables, which is n, equal to 6, because the relevant variables here 1, 2, 3, 4, 5, 6. So that's why it's here 6. The number of independent dimension, which is m, equal to 3, because there's a 3 type of the syllable in the syllable is, there's a 3 type of dimension, which is m, l, and 3. A number of non-dimensional groups, which is pi terms, the formula is n minus m. So basically 6 minus 3 equal to 3. Then step 4, you have to choose m equal to 3 dimensionally independent scaling variables. So we have to choose geometric property. In this question is diameter, kinematic property, and in this question is velocity, and then actually this is a fluid property. In this question is density. And then put all three in the pi terms. We have a 3 pi term, first pi term, second pi term, and third pi term. And then we have to put the a, b, and c. And then already pick 3 of the relevant variables, and there's a 3 remaining, which is we have already picked density, velocity, and diameter. And then the remaining is 3, 1, 2, 3. And then here take one of this remaining, put in the pi term. So that's why here they take this one, put in the first pi term. So that's why pi term equal to this one. And then considering the dimension of both sides, place the dimension of both sides, and then compare. After you compare, you can get the value of c, b, and a. And then after you get the value, you substitute in the here, and then you can simplify, and you will get the first pi term like this. And then the same procedure, the same step, and the same step you follow, and to get the second pi term and the third pi term, and then you will get this one. Okay, step 6 is set out the dimensional relationship. You have to write like pi term equal first pi term equal to function bracket second pi term and third pi term. Then you substitute the first pi term, second pi term, and third pi term like this. And then in step 7, rearrange if required for convenience. You have to rearrange here. They rearrange. They said the third pi term is the reciprocal of Reynolds number. So that's why the third pi term here they replace by RE. And then the pressure gradient, which is this one, dp over dx, is in terms of head loss. So they replace dp over dx here in this one equal to this one. So that's why here they rearrange the equation now. So the step 7 if required only. So that's the step. That's all the step. And yeah, thank you.